Okay, thank you very much. Thank you very much for your kind introduction, Georgian. And thank you very much for inviting me to great lecture series, Developmental Minds Global Lecture Series. I'm Tadahiro Taniguchi from Kyoto University. Okay, today I will be talking about developing collective minds, symbol emergence, and co-creative learning via collective predictive coding. This is an important term. So this talk will cover two main topics. First, I will introduce the collective predictive coding, CPC in short, a CPC hypothesis, as a foundational background theory. Then, based on the hypothesis, I will present our recent work on co-creative learning, which proposes a new human-in-the-loop machine learning method. This part is based on our relatively new preprint, which is available on arXiv now. Okay, so before diving into today's main topic, let me briefly introduce the idea of CPC hypothesis, which I proposed last year. So this hypothesis extends the idea of well-known predictive coding to social and linguistic phenomena. So it states that simple systems, including language, are formed through collective predictive coding by humans. In other words, the human society, which can be regarded as symbol emergent systems technically, can be understood as a social representation learning system. So as a result, the information of the world may be encoded in the distributional semantics of our language. So, okay, let me, before I begin the main part, the, I plan to introduce myself using this slide, but before the presentation, Yoshchen introduced me so very in detail. So maybe I should skip this slide. So, but basically, I am from the AI and robotics field, especially developmental and cognitive robotics. And also, currently, I'm also serving as a chair of the IEEE Cognitive and Developmental Systems Technical Committee, which hosts this lecture series as well. Okay, and this is a developmental mind lecture series. Let me mention one more thing. The Professor Angelo, who has spoken in this lecture series before, wrote this book. His book, Developmental Robotics from Babies to Robots, is a foundational text. And as you can see on the side, I, along with Professor Okada and our colleagues, read the Japanese translation of this book. And through this work, I have also served as a kind of one of the introducers of developmental robotics in Japan. Okay, let us get into the introduction part. So, since around 2010, more than 15 years ago, our community has been studying symbol emergence in robotics, or SER. SER takes a constructive approach to symbol emergence systems, inspired by developmental robotics. The core idea is to understand the emergence of symbols, including language, in human society by building developmental robots that acquire, invent, and share language based on their own real-world physical and social experiences. So we have developed many unsupervised learning methods for multimodal object categorization, concept formation, and language acquisition from speech signals to better understand human developmental cognitive systems. So most of our methods are based on probabilistic generative model. In other words, predictive models. Okay, let's look at this diagram, which illustrates our concept of symbol emergence system. So we model this as a dynamic interplay. There is a bottom-up organization process where interactions with environment shapes understanding, and a top-down constraint, top-down constraint process where the established emergent symbol system influence individual cognitions. Okay, the first critical component, first important component in this model is representation learning or world modeling by individuals. This is a process where each agent, be it a human or a robot or AI, builds their own internal representations or internal models through their unique experiences. So this is just an image from a time-lapse video of an infant. Visually represents the core mindset of developmental robotics, I think. This is cognitive systems that explores, learns, and develops through interaction with their environment. So this infant is actively explore the world, collecting multimodal data through physical interaction. Through this autonomous process, he or she acquires knowledge, learns to predict the result of actions, and gradually behave more efficiently. And this is the very process that supports individual representation learning or world modeling. So what computationally drive this exploration? I think predictive coding or active inference or world modeling are the key concepts here, I think. So actually, as a part of our line of research, we have been working on world models and predictive coding. So we have published several survey papers and perspective papers on these topics. For example, that we wrote this survey paper co-authored with many friends in the community of developmental robotics, the world models and predictive coding for cognitive and developmental robotics, frontiers and challenges. And also we wrote a paper about the world model learning and inference with Carl Friston. He served as the first author. So while I won't dive too deeply into this specific topic today, so yes, so let me skip this. And but in particular, in developmental and neural robotics, I want to mention the one leading figure. Professor Jun Tani has proposed the idea that brain functions as a predictive machine from the position of the viewpoint of developmental robotics. Through bodily interaction with the environment, it constantly generates predictions about what will happen next, and update its internal model based on prediction error. This is a kind of inference process. His hierarchical recurrent neural network models demonstrate how multiple timescales coexist: fast dynamics for low-level sensor control and slow dynamics for higher-level interaction, intentions, and planning. Furthermore, as his work suggests, when language is introduced to this system, it provides top-down influence or modulation on higher-level intentions, guiding action generation and interpretations. So this provides a widely accepted understanding of how language constrains our individual predictive minds. But where does this powerful language come from in the first place? That is the question. To answer this question, I introduced the idea of simple emergent systems. Language is not something that is given from the start. It is created within society and comes from others. It emerges from the groups. This slide shows the complete picture of a simple emergent system, while we've looked at the representation learning by individuals. Agents also interact socially through semiotic communication. So it's through social communication that shared symbol systems emerge across a group. We call this symbol emergence by groups. So this emergent symbol system then acts as a top-down constraints, as we saw, as we So in the previous slide, influencing the individual perception, communication, and the behaviors of our agents. So the simple emergence system framework emphasizes this interplay between individual learning and collective emergence. After proposing this descriptive model from the viewpoint of emergent system around 2010, 15 years ago, I have been studying this system to uncover the fundamental mechanism of human cognitive and collective intelligence in terms of symbols and language. So actually, the emergence of language is a long-standing research topic in this field. The researchers have been studying constructive approaches to language evolution and emergent communication for a long time. As this slide illustrates, we can see two major areas of this research. First, the kind of classical approach from the 90s to mid-10s. In this era, researchers like Luxtel, who is a pioneer of language game-based experiment, such as Talking Heads experiment, where agents form the categories and share sign through interactions. Second, the modern, the deep learning-based, revival starting from around 2016 or something like that. This trend was rebooted by influential paper using deep multi-agent reinforcement learning and referential games. So this field is also connecting to the discussion around large language models recently. However, keeping these important approaches in our mind, let me introduce another line of approach that we have been developing. So, okay, let's get into the next section. Let me introduce the Metropolis Hastings MH naming game, which we previously proposed. So while naming games have been around for a long time, so as we saw in the previous slide, this is a kind of qualitative update. So it is a type of language game built on a solid mathematical foundation. How does it work? So here is the outline. First, in the perception phase, the speaker agent and the listener agents observe the same object and infer their internal representations. We assume joint attention here, which is crucial for human language acquisition, as the people researcher in developmental robotics knows. And next, in communication, the speaker probabilistically utters a name for the object. So the listener then determines if it accepts the naming with a certain probability, which depends on its current belief state. Specifically, this probability shown in the equation on the slide reflects how well listener's belief matches the name proposed by the speaker. So if the listener agent does not find the incoming sign believable, it can reject the proposed naming. This ability to reject is crucially important. So third, in the learning phase, after the communication, the listener updates its internal parameters related to representation learning and naming. Okay. Finally, in turn taking, the speaker and the listener alternate their role and the game continues. Overall, this is a very simple game. But importantly, as I said, this game has a solid mathematical basis. Okay, let's dive into the detail. Maybe this might be somehow complicated, but if the acceptance decision is made according to this probability, then we can mathematically prove that this naming game is equivalent to the Metropolis Hastings algorithm for approximate Bayesian inference of the shared latent variable shown in the figure on the left. Let's begin with this graphical model. So here, OA and OB represent the visual observation or as a multimodal observation of each agent. They are the kind of visual input. Z the internal representations, the latent variables, in other words. Okay. So, and we also assume there is a shared variable W, which serves as a prior for these two observations, two variables. So if we treat W as a latent variable of a single agent, this graphical model becomes very similar to multimodal or multi-view variational autoencoder, or some other multimodal representation learning system. So if two agents' brains were directly connected and could use both observations to update W, so this variable would encode the combined information from both agents' input. However, in reality, they are independent cognitive systems, especially if we consider this as a kind of constructive model of humans, that our brain is not connected, are not connected. Okay, so let's introduce that kind of trick. Algorithmically, we can decompose the model into two parts. And the left-hand side represents agent A. Right-hand side represents agent B. Then we consider an alternative inference method for W. So now think about the sampling process. Agent A proposed a candidate latent variable WD by sampling from its posterior distribution. The proposed value is passed to agent B. And if the acceptance probability is designed appropriately, this process becomes equivalent to the Metropolis-Hastings algorithm, which is a type of Markov chain Monte Carlo, MCMC, under some condition. This guarantees that shared signs are formed and the category or some representations emerge among agents to approximate posterior distribution over W. Now, this has huge implication. I mean, in other words, by creating language or by creating the shared external representation, we can achieve a kind of cognitive integration equivalent to connecting the brains. So this is very interesting. Where we proposed the MH name game, we conducted an experiment to validate this idea. We use, in the first experiment, we used the MNIST dataset. Crucially, agent A observed the original MNIST data, and agent B observed the same images, but rotated by 45 degrees. This setup illustrated in the graphical model that simulates a scenario where two agents have heterogeneous or information by observing the same object, but from different directions. Okay, so the goal was to see if the Metropolis-Hastings naming game could allow them to integrate their two different views and form a shared coherent set of categories, shared names. To verify this, we compare its performance against several control conditions, such as non-communication or acceptance. So here is the experimental result. So if the agent do not communicate, their performance in clustering and sharing sign is something like this. So the kappa represented to what extent they could share signs. So they can kind of to what extent they could form a kind of shared vocabulary or something. And actually, when they perform Metropolis-Hastings naming game, so actually they both of them are students. They are not the kind of the knowledgeable teacher, but they can interact. So if they play Metropolis-Hastings naming game, the performance increased. This improvement occurs because in this learning process, the representation learning depends not only on a single agent's observation, but also on both agents' observation. theoretically. This integration of richer information leads to better result. So in other words, Metropolis Hastings interaction between agents enables them to integrate their perceptual information as a kind of collective mind, resulting in more effective modeling of the world and better internal representation learning. So the experiment shows interactive communication like the MH naming game allows agent to integrate information and build better representation, especially the external representation. That's a symbol system. So this brings me to the core theoretical background for my talk, a theoretical idea. That's CPC. This hypothesis extends the idea of predictive coding to social and linguistic level. And now let me introduce the CPC hypothesis, the kind of the dynamics of CPC step by step. So first, let me illustrate this figure. First, let's start from predictive coding or word model learning. Because there is a person, this is a kind of individual activity. There is a person. They internally have internal representation, or we can call that word model or internal models. We are living within the action perception loop. This is, I'll say, this is very popular figure, I think. That in many presentations, we can see this kind of slide. And this is very roughly speaking, it's a kind of inference process, updating the internal models, perceiving, the recognizing something. But importantly, we humans, we are so many. We are not alone. So, and we can introduce many agents here. So they are interacting with the environment. But so this slide assumes something weird. So each individuals are independently interacting with the environment. So somehow each agent is informationally independent. Isn't that strange? So actually we have many social interactions, and especially we use language and signs to communicate and coordinate actions and so on. The following, the the collective predictive coding hypothesis, through language game, we can form language-like social representations, external representation through the learning process. I think through this process, we model and adapt to the world collectively. So this figure shows that each agent collaboratively form some, symbol systems. So here, the subjects are people. But I think it's very interesting to take another view. But here, let me take another view. Until now, we believe each person is an independent and autonomous agent. But let's change the viewpoint. First, language is here. A symbol system is here. Language is a kind of autonomous system. And they have sensors. That's us. Language uses us to model the world through interactions. From this viewpoint, we are subordinate to the language system. Actually, this kind of view is often mentioned in sociology and some other academic field. So, okay, I think this kind of dual viewpoint is very interesting to extend our view of cognition to the social level. So collective minds, in other words. So actually, this dual view brings us to the formalization of the CPC from the viewpoint of free energy principle. So based on a generative model representation of CPC, we can naturally derive variation of free energy. Following the idea of free energy principle, interestingly, the final form can be divided into two parts. The first is an ordinary variation of free energy. This is a sum of variation of free energy of a number of agents. In addition to that, an interest term pops up. We call this the collective regularization term. This term tries to align agents' external representations, like symbols, W, with each agent's internal representation, Z. So with this term, the problem of minimizing individual free energy becomes the minimization of free energy of a single total system, kind of super agent. I think this book can extend the free energy principle from the individual to the collective level with a clear relationship to emergence of simple systems and language. So actually, on the basis of the free energy of the CPC framework, we can naturally connect it to the active inference. It extends individual expected free energy by incorporating a collective term. So this formulation allows us to consider active inference motivated or guided by emergent language. Future work includes, and I haven't write any paper, any the paper with experiment or something. So but the future work includes exploring this concept as active inference at the group level, potentially framing it as collective curiosity or something. Okay, so following the original study, we have continued to explore the MH naming game and emergent communication based on probabilistic genetic models. We published many papers, expand on to multiple agents, not two, but 3 or 4 or more, and expansion to the compositional language. So naming game just treated the kind of a word-like representation, but a sentence or something, and continuous signals as well. And also this can be extended to the multi-agent reinforcement learning settings. And so that we can deal with the coordination, agents coordination as well. Okay, and the expansion of a language game. We use the Metropolis Hastings algorithm, but other alternatives could be implemented. Okay, so maybe, but of course, I don't have sufficient time to talk about this in detail. But let me introduce one thing, one very recent, the preprint. It's still under review, but on archive now. So the Matsui et al. He is a former master student of my laboratory. Extended the Metropolis Hastings naming game to image captioning using visual language models. So they introduce language model GPT-2 into the caption generation process. In this scenario, agents were pre-trained on different datasets and attempt to adjust their expression through communication. And not only expression, but also internal representation. So this approach enabled agents to learn from each other while preventing catastrophic forgetting. Okay. And I have been talking, I have been talking about not only collective mind of artificial agent, but of humans. So I want to say that the CPC is model of human language emergence, but we did not have clear evidence supporting that the people actually perform this kind of inference process. So building upon the theoretical foundations, our earlier work, Metropolis Hastings algorithm in joint attention naming game, experimental semiotics study. Okay. On this slide, you see the setup of the experimental semiotic study. We designed an experiment to test whether human participants, when playing a game similar to the MH naming game, would follow the acceptance probability calculated by the MH algorithm. So the result, as shown in the graph on the right, were positive. We found that the human acceptance behavior indeed to some extent, mostly aligned with the theoretically derived the MH acceptance probability. This is a crucial finding because it suggests that human, to a certain extent, follow similar patterns to Metropolis Hastings naming game, providing empirical support that the idea that human behaviors on symbol emergence might follow a CPC-like mechanism. So this paves the way for our current research, integrating AI and human into this framework, so-called co-creative learning. Okay, let's dive into the final part. So, co-creative learning. So, a simple way to introduce co-creative learning. Co-creative learning is a kind of new word, new term, is to view through the lens of Metropolis Hastings style interaction between humans and AI. So this slide illustrates exactly that agent A, human, and agent B, AI, engage in the same semiotic communication, the same naming game. So we've been discussed. So why this kind of research can be meaningful? So actually, considering this kind of framework is important in the current generative AI era, I believe. When we talk about the AI alignment, especially in the era of LLMs, the dominant idea is often about making AI system follow human instructions and values. This is a unilateral framework where human knowledge is treated as a ground truth used to override the AI's internal knowledge, as this slide illustrates. However, this traditional unilateral alignment has significant limitations. For example, AI systems already excel beyond average human performance in many areas, possessing distinct and often superior domain knowledge. Furthermore, human and AI inherently have heterogeneous knowledge. Our way of understanding and processing information are fundamentally different. So, as embodied AI agents start exploring the world autonomously, it becomes questionable whether we should enforce our existing human knowledge and values as a sole ground truth. Perhaps instead of simply overriding, we should respect the AI's perception and knowledge to bring our collective knowledge to a better status. So, at the same time, in reality, we already observe a significant bidirectional inference. So large language models, for example, actively impact human language use and decision making, as shown by recent studies. This mutual influence clearly highlights the limitation of the perspective of purely one-sided alignment strategy. Therefore, looking beyond the current generative AI era, it is important that we establish the new system theory, principle, and learning method to achieve through the human-AI symbiosis, considering bidirectional alignment or teaching. That can be called co-creative learning process. So to position co-creative learning more intuitively, let's briefly and roughly review existing traditional unilateral machine learning framework. Or in the very roughly speaking, in supervised learning, the human human's perspective, this is the P, xn, x is null kind of observation, and Sn is sign or category, label or something. Okay, so the human's perspective effectively serves as a ground truth or target or reward for the AI to learn from. The AI's understanding is therefore fundamentally bounded by the human's perspective. In unsupervised or self-supervised learning without human teacher, the AI agent learns in isolation, inferring knowledge solely from its own observations. So in this case, its understanding is bounded only by the limits of its own perceptual data. A key takeaway from both these traditional approaches is that the only partial information fundamentally either from human or AI is used for learning process or symbol formation process. So this highlights a critical limitation. Neither approach fully leverages the combined potentially richer information available when human and AI interact. So this brings us to our proposed new bilateral framework called creative learning. Here the goal is not for one agent to teach the other, but for both to engage in bilateral message passing through language game and communication to integrate their partial observations. Instead of treating one agent's perspective as a sole ground truth, the learning target for the dyad becomes the true posterior distribution. Conditioned on the joint observation of both agent and human. This is a crucially different point. By integrating their distinct and partial information, this approach allows emergent shared understanding to surpass the knowledge that either the human and AI could have formed alone. The diagram on this slide illustrates this mutual interaction and the formation of a joint, more complete understanding. Okay? So given this insight, we then move to the core of our current work, the realization of collective predictive coding within human-AI collaborative system. As depicted in this graphical model, we envision a system where human and AI agent, each with their partial observation, engage in bilateral message passing through language games or communication. So this interaction facilitates the formation and inference of shared understanding. This is what we define as co-creative learning. Okay. So to be precise, we formally, and in the preprint, we formally define co-creative learning as an interactive, decentralized Bayesian inference process. So what we maybe you don't need to read the detail, but the important things is that the human and AI try to collaboratively decrease the collective free energy. Okay, the collective free energy somehow that it's some representation of misunderstanding or something. So by reducing collective free energy, we can we can infer the posterior distribution, collaboratively. So actually, as I mentioned, MH naming game, that kind of naming game or language game can reduce this free energy. Yes. So, okay, to validate this idea, we conducted an experiment. Yes. In this experiment, a joint attention-based MH-like naming game was played between human participant and the computer agent. The central question we aimed to answer was, can the human and the computer effectively integrate their respective partial observations through this naming game, thereby engaging in decentralized Bayesian inference, or as we term it, co-creative learning. To ensure this, each agent was given only a partial missing subset of a fully observable, the observational information. So maybe it's better to introduce a kind of the experimental setting in that paper. Okay, the stimuli consist of images depicting a circle with a radial notch. Okay, These were generated based on five-dimensional vectors, the feature vectors, and sampled one of the three ground truth Gaussian distribution. And using the CIELUV color space, which is perceptually uniform, and the parameters were chosen so that categories were overlapped significantly in the partial observation space. For human, human participants asked to categorize these, and the agent has to categorize these. So very difficult for agent to distinguish 0 and 1. And for humans, it's very difficult to distinguish 1 and 2. So, and this stimuli were given to a human and agent one by one, and they try to categorize them while communicating, using the unknown symbols. This is a very challenging task. So, okay. So the experiment, we recruited 90 participants and blah, blah, blah. We compared the three conditions, MH groups, and another is always accept group, And in this setting, for example, when the human participant says, "Oh, this is category A," okay, the agent has to follow, has to learn that category, and group 3 is always rejected. So even if the human participant say, "Oh, this is B" or something like that, agent simply ignores the human's suggestion. Okay, this is corresponding to the unsupervised learning by agent, and always accept corresponds to supervised learning. Okay, setting, and this is the result. And actually, that ARI represent the kind of clustering performance. Okay, the key finding is that participants in the MH group achieve the highest categorization accuracy and sign agreement, particularly on the AI side, when compared to both the always accept and always reject group. This indicates that the MH-based interaction most effectively facilitated shared understanding between human and AI and collaborative modeling of the world. So this is to visualize these trends. This figure plots the mean ARI over 200 communication steps for both human and computer agent in the three conditions. Okay, you can clearly see that only in MH interaction case, so they form better categories, gradually. Okay. Okay. So and while this graph shows the accuracy, ARI, categorization accuracy, a deeper analysis, which I'm skipping for this time, to confirm this, the sign distributions in the MH group also show the strongest convergence to the target posterior distributions, as the theory suggested. Okay, so to summarize our discussion, our experiments show that human AI pair can successfully engage in co-creative learning via joint attention naming game. So the MH acceptance rule significantly improved the categorization accuracy and agreement compared to the always accept and always reject control setting. Furthermore, a crucial finding was that the human acceptance behavior, so this is naturally, we didn't ask the human participants to follow this kind of theory, but as a result, their acceptance ratio behavior align closely with the theoretically derived metropolis Hastings probability. this reinforces the idea that this mechanism enhances perceptual integration and effectively facilitates decentralized Bayesian inference within human AI dyad. This finding collectively suggests a promising direction for designing symbiotic AI systems, systems that run with humans by fostering emergent interaction-driven alignment, moving beyond the limitation of the traditional unilateral approach to AI development. Okay, so let's conclude. So in this talk, I introduced a collective predictive coding, CPC hypothesis. This is our computational theory for how collective minds, in some sense, develop, extending the free energy principle to the social level. We argue that this process, which functions as a form of decentralized Bayesian inference, like the Metropolis Hastings naming game, I showed you that in the engine is the engine of symbol emergence. The key mechanism is that it allows both human and artificial agent to integrate their partial and heterogeneous perceptual information, leading to share co-created understanding. Okay, so this is a co-creative learning is a new paradigm for human AI interaction, I think. So, which contrasts with traditional unilateral alignment, where AI just learns from us. Here, AI learns with us. So our human AI experiment provided the first empirical evidence for this. Okay, so we believe this bottom-up co-creative process offers a compelling alternative to top-down alignment, paving the way for a future and true human AI symbiosis and the co-evolution of new knowledge. So, okay, before finishing, I'd like to mention our new book. As I talked about, symbol emergent system theory is an academic field that explored how humans and AI can jointly create symbol systems, such as language and culture through physical and social interaction. So as you can see on the slide, last year we published the Japanese book, okay, about this topic. And today I'm happy to announce that the English version of my edited book titled Symbol Emergent Systems, an interdisciplinary discussion about cognition, language, and society is also scheduled to be published by Springer next week on November 19th. It is also open access, The Japanese book is not open access, but the English version is open access. Japanese publisher kindly allowed me to do so. So it's an interdisciplinary discussion that connects AI and robotics, artificial life, language evolution, autopoiesis, and philosophies like phenomenology. I think that it's very interesting topic for many of you. So if you are interested, I would be happy if you have a chance to take a look. And finally, and one final, very exciting announcement. So since this is a developing mind lecture series, I am happy to announce that the 2026 IEEE International Conference on Development and Learning, ICDL, will be held here in Kyoto, Japan, from September 15th to 18th, 2026. So I'm serving as the general chair for this conference. As many of you will know, Kyoto is one of Japan's most historic cities and a very popular tourist destination as well. So it also has a rich cultural and academic heritage. So we are very excited to host the ICDL community, ICDL here. So I sincerely hope to see many of you in Kyoto in 2026. You can find more detail at the conference website shown on the slide, and you can find it via Google or something. Okay, thank you for your attention, and I look forward to further discussion. Thank you very much.